Alright, hello Sophie and Linda. I hope you guys are doing well in my absence and that you had no trouble getting to this video. We're just going to do one section today because it is a little bit tricky, and this rounds off chapter 10. So this one is on proofs by mathematical induction and counterexamples. I'm just going to go through the examples and definitions in the book, but provide some explanation for them, and then do a whole bunch of examples on the video, and then you guys can try some for yourself on the homework. Alright, so first, what is mathematical induction? It's a way of proving stuff. So if you remember back in geometry class, you learned how to do some proofs. This is a different method by which you can do proofs. And it's kind of a clever way of doing it. So you start off by saying, if I can prove something is true at the starting value, and if I can prove that whenever it's true for one value, it's also true for the next value, then together those two things mean it must be true for all values. So if it's true at the beginning, and if being true in one place makes it true in the next place, then the first place it's true means the second place is true, and the second place means the third, and the third means the fourth, and it just means that everything is true. So our goal is to prove that a various collection of statements, the first one is true, and then that each one implies the next one is true. And proving the first one is true is a piece of cake. Proving that the second one is true is where the real challenge lies. So let's look at some examples. This example is already worked out for us, which is to our benefit, and then we're going to do a couple of our own. So this is kind of the format that they'll be in. Prove that this initial statement is true. That's our overall goal. So the left-hand side of the equation is the sum of all these terms. They're all cubics. And then the right-hand side of the equation is this nasty formula. And we're supposed to prove this is true. So by induction, we have to do two things again. We first have to prove it's true when n equals 1. So you literally just plug in n equals 1. This side, if n is 1, that means we're only keeping the first term. So this side is just a 1. And then if you plug n equals 1 in here, you get this expression right here. And if you multiply this out, you get 4 over 4, which is just 1. So therefore, we get 1 on the left, we get 1 on the right. So this is true for n equals 1. So that's the easy part. That's proving that the statement is true for n equals 1. The next part is more complicated. We have to prove it's true for the next step in a line. So the way that we do that is a little bit, the idea is, I think, straightforward, but the way that we show the work is very maybe confusing looking. So the first thing they do is rewrite the equation with a k instead of an n. So the only difference here is they change the n into a k in all the places on both sides of the equation. So here to here, here to here. Okay. The next thing they want to do is prove that it's true for the next term. So the next term on this side is going to be k plus 1 cubed, because the previous one was k, so the next one is k plus 1 cubed. But of course the golden rule is if you have to add this on one side, you have to add this on the other side. So the reason we're choosing to add this k plus 1 cubed is because it's the next term on this side. Now we have to take this whole expression, holy crap, we have to take this whole expression and make it look like this one, but with a k plus 1 and a k plus 1. So it's kind of good to know what your target is, okay? Your target is the same expression, only n is 1 bigger, yeah? So instead of n, it'll be k plus 1 here squared. And instead of n plus 1, if we make n into k plus 1 and then we add another one, we're going to have here k plus 2 squared divided by 4. So that's kind of our objective. This is what we're trying to get to. So how do they do that? Well, you can see here, they take this whole expression, they multiply this out. Actually, the first thing they do is get a common denominator. Sorry, they put this as a common denominator of a 4. Then they multiply out on the k plus 1, what the heck? Factor. Sorry, this is taking me a second. Oh, they haven't actually shown, oh, okay. They say that this one and this one both have k plus 1 squared in common, so we take that out front. That leaves behind a k squared in the first one, which is here, and it leaves behind a k plus 1 in the second one, which is here. A 4k plus 1 in the second one, which is here. So the 4 is right here. Of this k plus 1 cubed, 2 of them got taken to the front, and the other one is right here. then they can distribute the 4 in. They get this k squared plus 4k plus 4. And then this is a perfect square, which we factor, and we get k plus 2 squared. So you might be wondering, or you might be thinking, the first time I did this is what I was thinking. I said, okay, I can follow along with what they did. Fine, that makes sense. And I can see that, yes, this is 1 bigger than this, and this k plus 2 is 1 bigger than this n plus 1 was. So I can see that it works. But how in the heck was I supposed to know what steps to do to get me to this nice format? How was I supposed to know to factor this out instead of distribute or expand it, and get a like all these different steps that they do? How do you know what they are? And my answer to you is, I don't have a good answer, unfortunately. The more of them you do, the better you get at recognizing what to do. And a lot of the problems that you're going to have in the homework very closely follow these examples we're doing. That's why I'm going to go through all the examples. So try to see how those are very similar to these with just different numbers. Okay, going on to the next example. A different type of proof by induction. I mean, the same thing where you prove the first one is true, and then you prove that each one leads to the one after it. But a different class of problems is proving divisibility. Okay, so we're trying to prove that any number 8 to the nth power minus 1 is divisible by 7. So the first thing to say, I'm going to jump straight down to here. If something is divisible by 7, that means you can write it as 7 times some integer, or positive number. Okay, so what we want to do is we want to increase this side by 1. Now, the way that you can increase the exponent by 1, because remember we're trying to say that instead of an n right here, we're going to have a k plus 1. Okay, so we'll first change the n into a k. That's kind of the standard thing that they do. And then in order to make this into a k plus 1, this is a clever little trick you can do. If you multiply this side by 8 to the first power, then by the rule of exponents, you can add the power of a 1 and a k, and then you get k plus 1 as the new power. So this is a clever little trick. Multiply by the 8 to the first power, add the exponents, and you get 8 to the k plus 1. But of course, if you multiply one side by 8, you have to also multiply the other side by 8. So that's why they have this times 8 right here. And then they distribute this in, and we get 56 plus 8. But if you recall, the original formula was this power minus 1. So from this 56 plus 8, we need to move a negative 1 back over here. So they subtract 1 on both sides, right? So here we have now what we want. This side is exactly what we want. It's the same as the beginning, but instead of an n, we have a k plus 1, which means the next term up in the sequence. And then on this side, cool thing happens. After we subtracted 1 from the 8, this is now divisible. This whole thing is divisible by 7, so you can factor a 7 out, and we're just about done. So this is the correct left-hand side. And then here, because our original number r was some whole number, then 8r plus 1 is definitely some whole number. Okay, so this original number was divisible by 7, leaving behind a whole number. So this whole thing here, if we divide by 7, it leaves behind a nice whole number. And this is guaranteed to be a whole number because r is a whole number. And if you multiply a whole number by 8, and then you add 1, it's still a whole number. So it's a weird thing. You might be wondering, why the heck should I prove this? Well, it turns out in math, typically we don't like to use formulas or shortcuts unless we can prove that they're true. And so it's useful to be able to say, okay, let's actually justify why any of these rules or shortcuts that we're going to use are actually true. And there's a lot of uses for these kind of shortcuts in a whole range of mathematics. We haven't really seen many of them yet, but I promise that they're there. All right, one more example. This is by far the easiest example. So this is counterexamples. I'm going to gloss over it pretty quickly. The idea is, instead of proving something is true, you want to prove something is false, or in other words, disprove it. To help remember that a counterexample proves something is wrong, they've got this little vocabulary review for us. The word counter is the same as the word contradict, and that means something that contradicts it or means it's not true. So to prove something is a counterexample, all you have to do is find one example where it does not work. So you take some kind of formula, for example. You take this formula, and they say, let's prove this does not work. So you can just try guessing some value of n, and then plug it in, and if the two sides are not equal to each other, then you've finished. You've proved that it doesn't work. And so I'm not going to spend your time doing that right now, but they say the answer is n equals 3, so you could try plugging it in. If you plug in n equals 3, add up this side, and then add up this side, you'll see that they don't equal the same thing. So usually you just have to try plugging numbers, try plugging in 1, 2, 3, 4, and eventually you'll be able to find one that proves it doesn't work. That's all there is to counterexamples. Okay, so now we're getting to ones that the book has not already worked out, but I have worked all these out in advance so that I don't get stuck in this video. So let's go through a couple and see how you guys feel about them. Prove each statement is true for all natural numbers. So again, we have to prove it's true for the first one, and then we have to prove it's true for the next ones after that. So the first one we have to do is prove it's true when n equals 1. Sorry, my handwriting is going to be terrible because I'm using a mouse. So if n equals 1, on the left-hand side, I only have the very first term, 1, equals. On the right-hand side, I have 1 squared. So of course 1 equals 1 squared, so that's true for n equals 1. Now, to prove that it's true for the next term in the sequence, we're going to rewrite this as k. So let's write 1 plus 3 plus ... 2k minus 1. So that's the last term that we had so far, equals k squared. Now what we need to do in this case is prove that this is also true for the next term up. So I'm going to add the next term in the sequence. Well, what's the next term in this sequence? The next term in this sequence, 2k minus 1 was the term before, and each time you notice we're going up by 2, by 2, by 2. So what number is 2 bigger than this? So it's 2k minus 1, and then an additional plus 2 on that. That's going to give us 2k plus 1. Can you see that that one is 2 bigger than that one? But if we add 2k plus 1 on this side, we have to also do the same on this side, so we've got to add 2k plus 1 on this side. So now this side is 1 bigger. It's 1 term bigger than it was before, which is what we wanted. And we have to make this side look just like this, only 1 bigger. So instead of an n right here, it's going to have to be a k plus 1. Okay, but lucky for us, I hope you guys can see this is pretty straightforward. This is a perfect square of k squared plus 2k plus 1 is exactly equal to k plus 1 squared. And so this is also 1 bigger. So if we prove that it's true when n equals 1, and we prove that it's true when this side is bigger by 1 and this side is bigger by 1, then it must be true for all things. That's pretty cool. Alright, moving on to the next one over here. Here, instead of adding up the odd numbers, we're just adding up all the numbers. So again, let's prove it's true when n equals 1. So here we just have a 1 on this side. If you plug a 1 in here, you get 1 times 1 plus 1 over 2, which equals 1. So that's true on this side as well. Now we have to prove that it's true for the next term in the sequence. Okay, so on this side, we're going to have 1 plus 2 plus ... Then we change the n into a k. And then what's the next term that we want to add? I'll leave it blank right now and then write on this side n times n plus 1, close parentheses, over 2 plus blank. Sorry, I'm running out of space. So the next term we want to add on this side, after k comes k plus 1. If we add k plus 1 on this side, we also have to add k plus 1 on this side. Okay, now this side is definitely 1 bigger, so this side is good. I'm just going to say this side equals, now let's look over here. Let's, again, as I always say, it's good to know what you're trying to go for. So let's look back up here. If I make an n into a k plus 1, then this is going to be k plus 1. And this side's going to be k plus 2. Can you see that? Because it's k plus 1 plus another 1. And then the whole thing is over 2. So that's what we're trying to get to. And that's what we have right now. Okay, so here's a situation where you may not see how to get from here, what we have, to here. What we have to prove is that this and this are the same. So there's a couple ways you can do it. You can start with this one and prove that it equals that, or you can start with this one and prove that it equals that, or you can start with both of them and have them meet somewhere in the middle. So I'm going to start with this one because that's what I have here. I'm going to distribute this here and I'm going to get n squared plus n over 2. And then with this one, I'm going to make a common denominator of a 2. So I'm going to say plus 2 parentheses k plus 1 over 2. And I just noticed something that's a huge error on my part, but it's easy to fix. Easy to fix. On this side of the equation, I changed my n's into k's, but on this side of the equation, I accidentally left this as an n and an n. So we need to change this into a k and a k in the original one, and then down here a k and a k. I apologize. It doesn't change any of the math that we were talking about, but it does change this from an n to a k. Okay, let me go back to red. Right, so they now have a common denominator. I can distribute this 2 and combine like terms in the numerator. So I have k squared plus, here I have 1k, here I have 2k. So that's a grand total of 3k. And distribute the 2 onto the 1, I have plus 2. This whole thing is over 2. And remember, we're trying to get to this form here, which is factored form. So I take this numerator and I factor it. I can see it's going to be a k and a k. And then two numbers that multiply to 2 and add to 3 is a 2 and a 1. So now if I look at this and I look at this, I can see that they're the same. So therefore, this side is one term bigger, and this side is also one term bigger. And I have proven, therefore, that for any term, if it works for one term, then it must work for the term that's one bigger. And if it works for the first term, and it works for one bigger, then it works for all terms. So we are done. Sometimes you get to the end and you don't really feel like you're done because you're like, I don't even know what I just did. So hopefully it's clear, and if it's not clear, certainly you can ask me questions to clarify later when I get back. Okay, moving right along. The second type of problem was proving things are divisible. So these are a lot more straightforward because they literally follow identical to the example. Okay, we're going to rewrite this. Divisible by 9 means 10 to the k minus 1, so change n to k, and then make a 9r. So if it's divisible by 9, you can write it as 9r. Now the trick is, this minus 1, sorry, it's not an exponent. It's just a number. There we go. It's 10 to the k, or 10 to the n, and then minus 1 separately as a subtraction, not as an exponent. So I'm going to multiply this side by the base, which is 10. That way I can get a 10 to the k plus 1. But I have to multiply this side by 10. And I'm going to do this example a tiny bit different than the previous one because I think my way is a slightly bit better. If I distribute this 10 in, I get 10 times 10 to the k minus 10 equals 90r. Okay, this first part here becomes 10 to the k plus 1, which is what we wanted, right? 10 to the n becomes 10 to the k plus 1. I want still this minus 1 though. So normally when you're solving equations, you would go plus 10 plus 10. You'd add 10 on both sides. But that would just get rid of it. We don't want to get rid of it. We want to leave behind a negative 1. So I'm only going to add 9 on both sides. Okay, that way the negative 10 and the positive 9 leaves behind a minus 1. And then over here, I have 90r plus 9. Well, that's factorable. They have a 9 in common, which leaves behind 10r plus 1. Okay, and we're pretty much done. Except, what did I mess up again, you guys? I'm so sorry. I messed up again. It's so annoying. I wrote r instead of k. No, that's on purpose. I'm so sorry. We changed n into k. That's our term number. The r is just some number, whole number. So the r, let me remind you because I myself got confused. R is just representing that if the overall result is divisible by 9, it can be written as 9 times a whole number. So any number that's divisible by 9 can be written as 9 times like 5, or 9 times 6, or 9 times 7, whatever the result is when you divide by 9. Okay, so we are still in good shape. And this side is increased by 1. This side is clearly divisible by 9, because if you divide by 9, you're good to go and you still have a nice whole number right here. So we are done with this one. This one I'm going to skip to save time on this video. It'll be the same exact thing, but you'll multiply both sides by 4, because the base is 4 for this trick. And finishing off strong with our counterexamples. Pardon me. Okay, to find a counterexample, I mean the answer is already here for you because I got it from the teacher's book, but you're basically just trying to prove that it's not true. So prove that this is divisible by 4. So we could say 3 to the n plus 1. To be divisible by 4, we have to be able to write it as 4 times some number r. So let's just pick a number like n equals 5. If I plug this in, 3 to the 5th plus 1 equals 4r. 3 to the 5th power, I think that's 340, let's see, 3, 9, 27, 81, 243. So this is 243 plus 1 equals 4r. So that's 244 equals 4r. Well, if I divide by 4, that actually works. 244 divided by 4 is 61. Okay, so I did not prove it's wrong. In fact, I provided more evidence that it's true. So n equals 5 did not work. The fact that they say n equals 2 is an answer makes me think maybe for odd numbers it works, but for even numbers it doesn't. So let me try a different one. Let me try n equals 4. So we can go 3 to the 4th plus, sorry, not plus there, plus 1 equals 4r. 3 to the 4th is 81. 81 plus 1 is 82. And without going any farther, I can tell you that 82 is not divisible by 4. And so therefore we've proved it. So in here you get something that's not true. That's good. That's what you want. You proved it's not true. And so this one I'll let you try by yourself. In fact, it's not even true for n equals 1. Well, that's a piece of cake to prove then, huh? Maybe try to find a different one besides n equals 1. Maybe like n equals 3. Let's say 2 to the 3rd plus 3 to the 3rd equals 4r. 2 to the 3rd is 8. 3 to the 3rd is 27. Well, certainly, yeah, that's not, is it? No, because 8 plus 27 is what, 35 equals 4r, and 35 is not divisible by 4. So we've proved that that's a counterexample. We've proved that this is not true by getting something here where the r value is not a nice whole number, because to be divisible by 4, you'd have to have a nice whole number for r. That's it for the examples. Let me figure out what your homework is, and that'll be coming next. Okay, and here's your homework for this section. It's not too many problems because each problem maybe takes a little bit of time for you to think and puzzle your way through. And I'll also post this in the document so you don't have to copy it here if you aren't able to. You can get it from there. Alright, good luck solving these problems. They'll be due, I guess, the Monday when we get back. Or no, Friday. They'll be due Friday, I guess, because I'll be back at school on Friday and we can go over them. Alrighty, sounds good. Good luck. Take it easy. Bye-bye.